Enough. Okay. Chapter 12a. You guys can just watch that and make sure it doesn't fall very fast. Okay, so 12a is redox reactions. So a lot of the reactions we've been talking about so far are actually redox reactions. And redox reactions is just a way to track electrons. So redox is short for reduction. Oxidation. Reduction and oxidation do not happen independently. If there's a reduction, there's also an oxidation. If there's an oxidation, there's also a reduction. They always go together, okay? You can't just reduce something without also oxidizing something, okay? So redox is our abbreviation, and redox reactions are just a way of tracking the electrons in a reaction. Why do we want to track the electrons? We'll see when we get to batteries. The flow of electrons is current. So electrical current is the flow of electrons. So next week we'll talk, well actually in 2 weeks, after spring break, we'll talk a little bit more about that. We are going to do all the labs on Friday that include the battery labs. So you'll get a little preview of electron flow and electrical current. But we'll talk about this more in 2 weeks, okay? So what is an oxidation state?
It has a positive charge.
So oxidation state isn't an actual thing, okay? It's not an actual charge, except in the case of ionic compounds. But it's not, in a covalent compound, it's not an actual charge on the atoms. It's just some way we think of the atom, okay? So it's different than an ion. It's not an ion. It's just a way we think of the charges, their oxidation state, in order to help us understand the reactions. So an oxidation state for an ionic compound, like NaCl, is just the charge on the ion. Remember, an ionic compound is a metal bonded with a nonmetal. That metal gives its electron, 1, 2, 3, 4 electrons, to the nonmetal. Resulting in charges. So the metal gets a positive charge and is the cation. This should all be reviewed. The nonmetal gets a negative charge from acquiring electrons and is the anion. Okay, so those are ions, right? In the case of NaCl, the sodium gives up its electron and gets a positive charge. The chlorine gains an electron and gets a negative charge. An ionic compound, these are complete charges. That electron has completely left the sodium and gone to the chlorine in an ionic compound, okay? And what holds the sodium and chloride together when it's a solid is that magnetic attraction between the positive and the negative. When it gets into solution, what happens? It gets, yeah, in a polar solvent, it gets split apart, okay? So what's important with an ionic compound is to remember that there's a complete transfer of the electron. So its oxidation is really easy to determine. This is an oxidation state of 1+, and this is an oxidation state of 1-. So in an ionic compound, it's really easy to find the oxidation states. It's just the same as its ionic charge. If you had magnesium chloride, MgCl2, we can figure out their oxidation states in the reverse of that process we do when we do the little switcheroo, right? We know magnesium's from group 2, so we do 2+, and chlorine's from group 7, so it needs 1 more, and we do that switchy. You just do the opposite here. Magnesium's going to become 2+, chlorine is going to become this 1-, and then magnesium's going to become this 2+. Okay, so magnesium's oxidation state is gonna be 2+, and chlorine's gonna be 1-. Okay? What about in a covalent compound? In a covalent compound, in a covalent bond, covalent is the sharing of electrons. So unlike the ionic compounds that we just looked at, there's not a complete transfer of an electron. There's a pair of electrons that are shared between bonds, between elements. So in CF4, there's a pair of electrons represented by this line that's shared between the carbon and the fluorine. Each one has a pair of electrons. So how do we assign charges to a covalent compound?
Electronegativity.
Right, we look at the electronegativity of the atom. Now, what are our general trends for electronegativity on the periodic table? And what is electronegativity?
Top right is the
So as we go across the periodic table, we add protons, right? So if we look at the second row, that starts with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Each time we go one to the right, we're adding a proton. That increases the charge of the nucleus. So that nucleus is getting a little bit bigger and more positive each time you go to the right. So that's exerting more force, an electromagnetic force, on those electrons that are orbiting. So it's pulling on those electrons more, increasing its electronegativity. Okay? Now what happens as we go down the periodic table? We're adding protons, so we're increasing the charge of that nucleus, but we're also adding what as we go down?
electrons.
We're also adding electron
So more attracted to each
orbitals.
other.
So it's getting bigger, right? So the radius is increasing. So those valence electrons are further away. So the protons can't pull as hard on them because of the distance. Remember with the gravitational force, it's inversely proportional to the radius squared. So the distance makes a really big difference, okay? So as we go this way, to the right on the periodic table, and up on the periodic table, as we go up towards fluorine, the electronegativity increases. The ability of that nucleus to pull on the valence electrons increases, going up towards here. Okay, so the most electronegative element is fluorine. Why isn't it neon and helium? Because those are noble gases. So they're further up there, but they have their valence shells completed, so they're not reactive. So fluorine is considered the most electronegative. Okay? So, when we look at a covalent compound in which the electrons are shared, the electrons are going to spend more time towards the fluorine. Even though they're shared, the fluorine's going to pull harder on them. Remember, giving this a slight negative charge. Giving the carbon a slight positive charge. Okay, just like we drew in the water molecules, we can make a delta plus and delta minus on pretty much any molecule that has covalent bonds. And remember, these are called polar covalent bonds. Polar means that they're not shared equally. Any covalent bond between two different elements is going to be polar. So this is a polar covalent bond. And then remember from, I don't know, chapter 3 or 4, this molecule, it has 4 polar covalent bonds, but they all cancel each other out in their geometry. So the net result is a nonpolar molecule. Remember that? So the molecule itself is nonpolar, but each bond within it is polar. Okay? So we have our delta plus and our delta minuses. When we think of oxidation states, we're going to say that that's completely negative and the carbon's completely positive. It's not actually completely negative and positive, but for oxidation state purposes, we treat it as if it is. Okay? You guys understand the difference between an ion, which has a complete charge, and an oxidation state, which is just an idea or concept to help us understand oxidation and reduction reactions. So we know the fluorines are going to have these electrons, right? We're going to treat them as if they have the electrons full time and give them a -1 oxidation state. So when we're calculating oxidation states, we pretend that it has the electrons full time. So the fluorines are going to get a -1. Now there's 4 fluorines, so what do we need to do to the carbon in order to balance this molecule? Because this whole molecule needs to have a net charge of 0. So we need to give it a +4 to balance out those 4 fluorines. And you can see that if I take the electrons away from this carbon, here, 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 and here, I'm taking 4 electrons away, right? And that gives me a +4. Okay, so for HCl, this is a covalent bond between these two. Which one am I going to consider to be more electronegative? Chlorine. So that's because it's so much bigger and stronger than the hydrogen, and hydrogen so readily gives up its electrons. The hydrogen is going to get a +1, giving its electron, and the chlorine is going to get a 1-. How about aluminum oxide?
Oxygen is more electronegative.
Mm-hmm. So this is an ionic compound. We've got a metal and a non-metal. So we know this metal is going to give up its electrons. And we can do that little switcheroo. So we know the aluminum is going to be 3+, and the oxygen is going to be 2-. We can look at the periodic table for that too. Aluminum's in group 3, group 3A, and oxygen is in group 6A. So group 3A, we know it's going to give up 3 electrons, and then oxygen is in group 6A, it wants to receive 2 electrons. Okay? So that brings us to the rules for determining oxidation states. And I promise in 2 weeks when we go over batteries, this is all going to make more sense as to why we do all this. Right now it seems a little arbitrary learning these rules, but it'll make sense when we get through. So rule 1, we talked about for ions, the oxidation state is equal to the ionic charge. So a chlorine ion is going to have an oxidation state of 1-. A sodium ion is going to have an oxidation state of 1+. So whatever ion it is, it's going to have that oxidation state. When it comes to polyatomic ions, like NO3, this whole thing is going to have a charge of -1, and then you can figure out the oxidation states of the individual atoms. We'll get to that in a minute. Number 2, for elements, so just plain element like copper, iron, zinc, and homonuclear molecules. The oxidation state is 0. Okay? Now this is homonuclear molecules, not just homonuclear diatomics. So homonuclear diatomics are like N2, O2, F2, all the halides, Cl2. Those are homonuclear diatomics, but homonuclear molecules also includes O3, ozone. Okay, so anything that has an atom bonded to itself, whether in O2 or O3, F2, N2, anytime it's the same atom bonded to itself, however many times, like S sulfur 8, the oxidation state's going to be 0. Okay? Because there's no sharing of the electrons in a polar way. right? When we had carbon bonded to fluorine, those electrons were shared unequally, but when sulfur is bonded to sulfur, they have the exact same electronegativity. So the electrons are shared completely equally. When you have oxygen bonded to oxygen, even when it's oxygen bonded to oxygen bonded to oxygen, all three of those oxygens have the same electronegativity, so all those electrons are shared equally. Okay? Rule 3 is for molecules and polyatomic ions. The sum of the oxidation states has to equal 0. Sorry, equals the total charge. So like I was saying with the polyatomic ions, and I'm going to turn back to that chart so we can review those, because we use those a lot. So our polyatomic ions, like ammonium, this whole thing, the oxidation state of this whole polyatomic ion is 1+. Now the individual atoms within here, we can figure out. Hydrogen is always 1+. And so in order to end up, we've got 4 hydrogens. In order to end up with a 1+ on the whole molecule, we know that nitrogen must be 3-. No. Is that right?
4 minus 3 is 1.
Okay, thank you. I was like, maybe it's 5-. No, 3-. Yeah, so then we go up to 0 and 1 more. You helped me with the algebra. How about the hydronium ion? It's H3O+. So the whole charge on this is 1+. Oxygen and hydrogen. Hydrogen's 1. So that's 1+. We've got 3 of them. So this needs to be 2-, right? In order to get the whole molecule to end up as 1+. Let's do a -1. The nitrate, NO3-. Oxygen is generally 2-. So 2 times 3, that would be 6-. So then we need a 5+ for the nitrogen. Okay? Now one thing I want to note, you see nitrogen here is 5+, nitrogen here is 3-. Okay? Atoms can have different oxidation states depending on what compound they're in. So nitrogen's not always 5+. It can be pretty much anything depending on what it's bonded to. The only ones that are almost always the same oxidation state are hydrogen, which will always be +1, with one exception. And fluorine is always going to be -1. Okay? So that brings us to rule 4. Fluorine is always -1. And that's because it's the most electronegative element. Okay, hydrogen is always +1, except in ionic compound. Such as metal halides, not halides. What are they called?
Hydrides?
Hydride, thank you. Where is it? Metal hydride. Such as aluminum hydride and sodium hydride, which are a little bit rare. But in general, whenever you see hydrogen, it's going to be +1. Okay? So these are the 5 rules that are always true. Except we're noted here, where there's exceptions in the rule itself. Okay? And then the 6th and 7th rules are sometimes true, or mostly true, usually true, Oxygen will be 2 minus. And we saw that here, oxygen was 2 minus, oxygen was 2 minus. So it's usually 2 minus. And then group 7A, halides, are usually 1 minus. Like chloride, especially chlorine. But fluorine, chlorine, iodine, bromine, everything in that group 7As, usually 1 minus. Okay? So, fluorine, hydrogen, usually oxygen, and usually the halides will keep the same oxidation states regardless of what they're bonded to, but all the other elements can be any oxidation state. Okay? You need to go through the comprehension checks. Did you check them yourself? Comprehension checks 1 and 2. We need to go through those. Did you check yours, Tina? Okay. If you checked them, did you check them, Lena? Did you what time is it?
10:16.
And we have until
10:40. Yeah, 10:40.
And am I still on camera?
Yeah.
We still recording?
Oh, like last year.
Huh? 10:40. Okay, it's 10:15? 16? Okay. So, let's look back again at this. HCl would be aqueous, right? And we go to hydrogen gas plus chlorine gas. It's already balanced, 2 hydrogens, 2 chlorines. So what's the oxidation state of HCl, hydrochloric acid,
It's 1 and
or hydrogen chloride?
1 plus 1 minus.
So hydrogen is always 1 plus when it's in a covalent compound. Chlorine is usually 1 minus, okay? Now this is a homonuclear diatomic,
0.
so its oxidation state is 0. This is a homonuclear diatomic, so it's 0. So what happened to the hydrogen? It had a positive charge, now it has 0,
Gain an electron.
so it gained a negative charge.
So it got reduced.
So hydrogen gained an electron.
It's oxidation agent.
Which means it was reduced. Okay, and he told you to remember Leoger, right? But there's another one, oil rig, oxidation is loss. Reduction is gain of an electron. Is that one easier?
Or you can just think in terms of protons, like
But I think of like reduction, like
reducing protons.
it was reduced from +1 to 0. That's how I always remember it. But I thought this one was good given our location in West Texas, oil rig. So oxidation is losing an electron. Hydrogen gained an electron, so it was reduced. Reduction is gain. So the chlorine, what happened? Chlorine was negative, now it's 0, so it lost an electron.
So reducing.
So it was oxidized. So who's good at grammar in here? What type of verb is this? It was oxidized. Is it passive or active?
Passive.
This is a passive verb. So what's the active? What's the opposite of this? The active verb.
Yeah.
So it was oxidized, it reduced. It's the opposite. It was reduced, it oxidized.
Oh, isn't it called the agent?
So it is the reducing agent. So this is the active thing it did. This was the passive thing that was done to it, right? So in Latin, if you have your active and passive, that's your mood, right? I praise, laudo. I am praised. He doesn't want to talk about Latin right now. Laudato, he is praised. So this, it was reduced, so it was passively reduced, it was oxidizing, it was the oxidizing agent, the active. Okay, so these can be confusing, but if you just think about it kind of the long way, it makes sense, right? It's just you can kind of get lost in the terms, but if you think about it or write it out, when I always say when in doubt, write it out, it'll help you to remember it. So let's do an example that's from our experiment back in chapter 6. Experiment 6.3. Turn back to it. Experiment 6.3 was copper plating nails. So we had a nail that was galvanized. Which means it's coated in zinc. And we dissolved some copper sulfate, copper 2 sulfate. We dissolved copper 2 sulfate into water. And then put the nail in it. And what did we do? So we immersed the nail about 3/4 of the way and let it sit for 2 minutes. And then we took the nail out and observed it. And what happened? You guys remember? Andrew, turn back in your lab book to see what our results were. So what happened to the nail and what happened to the solution? 6.3.
The copper coated nail, but it came off, flaked off.
So what color was the nail? Did it turn copper colored?
It was green.
And what happened to the solution?
I didn't record it yet.
Okay, so the nail should have turned a different color.
It just turned it silver.
I think it turned copper color.
Yeah.
It was silver and then it turned copper color. And the solution changed from blue, copper sulfate was blue, to green. Okay? You need to take better notes. So,
You already graded this one, so I don't know.
what's our chemical formula for copper sulfate? How do we figure it out? So we know copper is what? What's its atomic symbol? Anybody?
See, what? It's what?
What's its symbol for
Cu.
copper? Cu. And what state is it?
It's a
How many
2+.
electrons? Yes, because it has a 2 here. So it's a 2+. And what's sulfate? From our chart of polyatomic ions, it's SO4, 2-. It's from our handy chart. Okay? So we put copper sulfate in the water, and it was blue. So that's CuSO4. Remember we did a little switch? They're both 2, so we can reduce that fraction to CuSO4. This is aqueous. And then we put in the nail, which had zinc on it. Elemental zinc, just metal zinc. Okay? And it was solid, right? Aren't you writing this down, Andrew? And what happened? We made, that nail turned copper. We made plain copper on the nail. And the zinc went and bonded with the SO4. turning the solution green. It was a different thing dissolved in the water now. What type of reaction is this?
Single displacement.
Very good. Single displacement. So it's like, what do you want to pick on today? Poncho? It's like Poncho has a girlfriend, and then who comes? Corbin comes along and steals that girlfriend, and Poncho's left single.
That sounds very right.
So that's your single displacement reaction. Remember what happens in a double displacement is if Poncho and Corbin both had girlfriends and they switch them. Okay, so what's the oxidation state of the atoms in this molecule? Well, we already know from up here.
0. Oh wait, there's 4.
The overall molecule is going to be 0, but the atom within, is it still on?
It's still recording. It's just
Oh yeah, it's still on, it's just running out of battery. Can you see now? Thank you. Okay, so remember in an ionic compound, which this is, even though it's a polyatomic ion, it's still an ionic compound. It's just whatever the charge is. So Cu is 2 plus, SO4 is 2 minus. What about zinc? There are no bonds. It's
yeah,
just
that's just whatever charge
it's just a
it
metal,
is.
so it's 0. It's just an atom, it's not an ion.
The the copper is 2 plus.
Now over here, our copper is 0. Now this is just a metal. It's not an ion, it's just a solid metal. Just like the zinc was, now the copper is. And here, SO4 we know is 2 minus. So we know that must be 2 plus. Okay, so what happened to the copper? It
It
went from 2 plus
Gain 2 electrons.
to 0, so it gained 2 electrons.
So it's reduced.
So copper gained 2 electrons,
It's an oxidizing agent.
so it was reduced. So it gained electrons, reduction is gain of electrons, Rig. It was reduced, which means it was the oxidizing agent. So copper was part of copper sulfate, so we just say the whole molecule. It was the copper in it, but since it came in a molecule, we say the whole molecule was the oxidizing agent. So CuSO4, copper 2 sulfate, was the oxidizing agent. What happened to the sulfate?
The opposite.
No, sulfate's 2 minus?
Oh man.
2 minus.
Yeah.
Sulfate was, in terms of redox reaction, was like the spectator here.
Zinc was opposite.
Zinc went from 0, where is it, to 2 plus. So it lost electrons, right? Oxidation is loss, oil. So zinc lost 2 electrons. So it was oxidized, which means it was the reducing agent. And it was just metal zinc here, it wasn't in a compound, so we just say zinc was the reducing agent. Okay? So we're gonna do a lab over that on Friday, and you should be able to identify which was reduced, which was oxidized, which was the reducing agent, and which was the oxidizing agent. Okay? Now, just for fun, let's look at the SO4 2 minus polyatomic ion. What are the oxidation states of these 2 atoms? According to our rules.
They have to add to -2.
So all of this needs to add up to
But
-2.
O4 is a -4 minus charge, right?
So oxygen is generally what oxidation state?
Not -1.
No. Tina?
-2.
-2.
So it's negative.
So it's generally -2. So 2 times 4 is -8.
So S has to be 6.
So S must be 6 plus. And if you look at the periodic table, S is in group 6, so that makes sense too, that it gives up 6 electrons. So let's do comprehension check 3, and then we'll be done. Isn't this fun, guys? It's like learning a new language. Maybe that's why I like chemistry, because I love foreign languages. Comprehension check 3. Let's look at SF4, sulfur fluoride gas plus fluorine gas makes SF6 gas. So right off the bat, we can see that fluorine is a what? Fluorine gas is a what? What type of molecule? Lena, do you know?
Homo.
Is your name Lena? Homonuclear diatomic. So fluorine is the most electronegative, but it's two fluorines bonded to each other. They have the same electronegativity. So their electrons are going to be shared completely equally. Okay? It's a purely covalent bond. Remember that term? It's not a polar covalent bond, it's purely covalent. So its oxidation is going to be 0. Neither one of those fluorines is going to have the electrons more than the other. What about this one? So in our rules, fluorine is always -1. So that's 4 negative ones. What does the sulfur have to be to balance this?
+4.
4 plus. So over here, what do we have? Same thing, we know the fluorine's always -1. And so that's -6. In order to balance that, we need to have a +6. So, what happened to our sulfur?
It gained 2 protons. So
No. Oxidation states are the tracking of electrons.
I know, but it gained 2 protons.
So we need to track it in terms of electrons. No. Sulfur lost 2 electrons.
So it was oxidized.
Sulfur is oxidized. So I should write. Sulfur lost electrons and became more positive. So it was oxidized. So it is the what? What type of agent?
Reducing agent.
Yep. So SF4 is the reducing agent. Since the sulfur comes in this compound, we'll use the whole molecule to say it's the reducing agent. And then what happened to the fluorine? These fluorines stayed the same, but these fluorines got more negative. So,
That was reduced.
the fluorine is reduced. So it gained an electron. So it was reduced. So F2 is the oxidizing agent. How about B? HCl plus KOH, so hydrogen chloride or hydrochloric acid plus potassium hydroxide. And what type of molecules are these guys? HCl and
Acid.
KOH. Yep,
Base.
it's an acid and a base. And what do acids and bases generally form when you mix them
Water
together?
and salt.
Water and salt. H2O plus what salt?
The chlorine and K. Chlorine, potassium, water.
Potassium chloride. Yes, so this is essentially a double displacement reaction, right? This chloride and this potassium are going to get together, and this hydrogen and the hydroxide are going to get together to form water. Okay. So what are our oxidation states here? In the HCl, this one's easy, right?
1.
1 plus
1 minus.
and 1 minus. What about the KOH? Potassium's 1 plus. OH, we know from our polyatomic chart, is 1 minus. And if you look at this by itself,
-2 plus.
right, it's going to be 2 negative and 1 plus to form an overall, a net -1, okay? And then over here, what are our oxidation states?
-2.
Hydrogen's always
2
plus 1 when it's in a covalent compound. oxygen is generally -2, because that's 2 hydrogens, so that's +2, -2. And then this is ionic compound. So what happened to our hydrogen? It's +1 here,
Nothing.
it's +1 here, +1 here. Chlorine is
Nothing.
-1, -1. Potassium's +1, +1. Oxygen is -2, -2. So none of them change their oxidation states. So this is not a redox reaction. So if you read through all the examples in the book, you should have noticed a trend that single displacement reactions, or like the copper sulfate plus the zinc, and that's a single displacement, or formation and decomposition reactions, are more likely to be redox reactions. Double displacement reactions are more likely to not be redox reactions, okay?
That's an acid and base reaction.
It's an acid and base, which is essentially a double displacement. Okay? So that's just a general trend, not always true, but if you read closely, you would have noticed that. So let's do copper solid plus HNO3 aqueous plus hydrogen atoms, which we must have gotten from an acid, makes copper 2 plus NO gas and H2O liquid. So how can we balance this equation first?
Put a 3 on the NO.
Start with 2 on these. Well, it was given balanced.
Well,
Are we at, what time is it?
We have 3 minutes.
Okay, so it was given balance, we'll just, since we're running out of time, I'll just quickly balance it. 6. Okay, so what's the oxidation state of our bare metal? Just elemental metal,
0.
0. What's the oxidation state of hydrogen in a covalent compound?
+1.
1 plus. Nitrogen, so we know this whole thing, NO3, is -1, right? So these oxygens are gonna be 2 minus times 3 is
5.
6, so this has to be 5 plus. And then our hydrogens are always +1. Now here we have a copper ion. They didn't include whatever was bonded here would have gone over here, the spectator ion, right? So this is given as 2 plus. Oxygen is 2 minus, right? To balance that, we need a 2 plus. And then water, this is a 1 plus and a 2 minus. So what was oxidized and what was reduced? What happened to the copper?
Copper was reduced.
Copper went from 0 to 2 plus,
Oxidized.
so it was oxidized. So it's the reducing agent. Hydrogen stayed the same, +1. Oxygen stayed the same, 2 minus. What about nitrogen? It went from 5 plus to 2 plus. So it was reduced with 3 electrons. And then copper would be the reducing agent. HNO3 is the oxidizing agent. Okay? So this is not quite a double displacement because there's 3 agents, but you guys have any questions? Okay, we'll see with our experiment 12.1, we're going to see that the solution is going to change colors. When metals get oxidized, the color of the solution can change. So we'll see that. We saw that with our 6.3 and we'll see it with 12.1.